As we move through life, we encounter numbers that are obviously significant. For example, do you recognize this one, 3.14152? What is this? Yes, it would have been pi if that digit had been 7 instead of 4. And the next, 0.07, 007, what is that? Obviously, James Bond. But it turns out the surface tension of water at 25 degrees Celsius, typical temperature at Oxford. And if you know that number, you understand lots of things. For example, when you shower, there are lots of droplets that are hanging from the glass pane and so on. And that's all understood, how large those droplets are in terms of 0.07, something that you can remember for the rest of your life. Now, and yet, some other times, I meet numbers which look significant, but which we cannot quite place. For example, when I saw this number, I knew it meant something in my life, but I cannot really remember what it is. So I mobilized my entire scientific education, and I tried to calculate this number from that number, and I really don't see where it comes from, although I know I have seen it somewhere before. But this morning at breakfast, finally, eureka, I know what it is. It's, of course, the telephone number of the Mathematical Institute at Oxford University. Now, the leitmotif of this lecture is 2.5. What is that? Well, you'll be happy to know that is exactly a number between 2 and 3. And I'd like to convince you that this is, in some sense, more than metaphysical sense, the dimension in which paper, membrane, surface, any such thing evolves, lives, and continues to surprise us. It is between the dimension 2, which is intrinsic to the paper. It is obviously a two-dimensional object, but it's also important that paper lives inside a three-dimensional ambient space. So that's the extrinsic. And this is the interplay between the intrinsic and the extrinsic, which will be really the weaving theme. In order to start, I shall play a little magic trick on you. I brought here a coaster, a circular one, and then a piece of paper, which is where I put the hole. And now I put this like that, and I can pass the coaster, circular coaster, through the hole like so. It is really going through, you see. And I haven't started cheating yet, so it is really going through. But when you put one next to the other, obviously the diameter of the circle is greater than the diagonal of the square hole. I did not stretch, let alone tear. And yet something larger goes through something smaller. You see, I can even pass it backwards from here, and it is really going through, as you can see. And what is going on? Large thing is going through a smaller thing. So how is this possible? Because you are such a nice bunch of people, I'd like to reveal the secret for free. Usually I pass around the hat. But you see, when you fold the paper like this, the largest gap that I can take advantage of is this one, which used to be the diagonal of the square hole. But that's not all I do. I grab this sheet of paper, and then I twist. As I twist, you might see in the camera that the part of the paper is rising away from the two-dimensional plane into the three-dimensional remaining residual dimension. And as those two segments are aligned, I squash and crease. Then the gap that I have created is no longer the diagonal, but it's actually the sum of those two sides. And if you remember Pythagoras, you have gained an extra factor of about 40%, square root of 2 minus 1. So that's how you can pass this through. Although the square seems to be smaller than the diameter, the secret was to make a hole whose diagonal is shorter than the diameter, but whose sum of the two sides is longer. And you can see that this kind of thing was possible, although at first sight it was impossible, because we escaped into the ambient 3D and then came back down into 2D. And this extra freedom of going in and out is going to be really important for us. Do you recognize this man? He's the most romantic figure in the history of mathematics. Perhaps you know him. So that's, who is this? Évariste Galois, thank you very much. And he died at the young age of 20. Now, Professor Trefethen is thinking, oh dear, Tadashi can't do arithmetic, because if you subtract 11 from 32, it's 21. But he died shortly before his 21st birthday. So he left a gigantic legacy for all of us. And one of the simplest things that he taught us to solve is a Greek problem, a problem going back to the ancient Greeks. And this is the problem of trisecting an angle. You might have some recollection of taking an arbitrary angle and dividing that into two equal parts. That's the bisection. With ruler and compass, it's very easily done. But can you do 3 equal parts, that is trisection of an arbitrary angle. To be sure, of course, there are angles that can be trisected. For example, the flat angle of 180 degrees, 60, 60, 60, no problem. But that's not the problem. The problem in question is there a universal algorithm using ruler and compass, straight edge and compass alone, which given any arbitrary angle under the sun, automatically trisects it into 3 equal parts? And if you learn a little bit of mathematics, for example, first year or two of mathematics, you learn that in fact there are angles that you cannot trisect with ruler and compass alone. For example, something as simple looking and innocent looking as 60 degrees cannot be trisected. However, there is an ancient art in Japan, which is more and more popular nowadays, called origami. Ori means fold, and kami means paper. So folding of paper. And with origami, you can do all angles. Here is one example. You can see actually instead of the, how do you bisect an angle? Let's say that your angle is given as a corner of a sheet of paper. Actually, corner of a sheet of paper is usually 90 degrees, isn't it? But let's say that your angle is given there. And how do you bisect it? Well, it's very simple. You just fold over until the edges are aligned. You just align the edges, you negotiate, and once they are nicely aligned, you crease and open, and you see this beautiful line that comes out of the corner, and that is the bisector of the angle that divides the angle into 2 equal parts. Nothing is simpler. Well, trisection is no harder because you just fold over, you overshoot, and then come back, and you make this 3-fold sheet, and then you just align, you negotiate the corners, and then you align until they're well aligned, and you crease, and when you open, you have to see those 2 beautiful lines that are coming out from the corner. Those are the trisection lines. And n section is no harder. You go back and forth, you have an n-fold sort of crease, and then you open. Many people don't like this negotiating the sides because they want to have every operation to be determinate and discrete. But in fact, one of the powerful points of origami, one of its secrets of versatility, is that you can seek for an optimum answer among a whole continuum of continuous parameters. And that is, in fact, very important. Now, next, do you recognize this person? He looks rather grumpier than the first one, but he is no less of a giant in mathematics. That's Carl Friedrich Gauss. And he, too, left a lot for us to think about. He stands at the junction between the 18th and 19th century. And one of the simpler problems that he allowed us to solve is this problem. You might recall drawing a regular polygon with ruler and compass. For example, I showed a regular trigon that is called a equilateral triangle. You just draw a segment, you plant the pivot of the compass at one end, and you just draw a circular arc. At the other end, you do symmetrically, and that intersection is the third vertex that you connect to the ends in order to make an equilateral triangle, regular trigon. Can you draw a regular n-gon with ruler and compass alone, with n for whatever you like? Yeah? And you probably suspect that the n has to be of a very special type. It's slightly inaccurate what I'm saying, but this is what the answer is. Forget about the power of 2 in the first place. The n has to be essentially a product of primes of distinct forms. These are very, very strange primes of the form 2 to 2 to something plus 1. These are called Fermat primes. And if you plug in various values of something, you get this sequence 1, 3, 5, 15, 17, 51, and so on. Some of these are primes, some of them are not. Those in boldface, 3, 5, 17 are primes, later on to 157. And if you multiply those primes, never repeat in the same factor twice, but multiply them, and multiply that with some power of 2, that's a number that can be constructed by ruler and compass, and regular n-gon, and it's even and only. Yeah. The power of 2 is easy because once you have constructed some regular n-gon, you can always divide each of the angles into 2 parts. Bisection is easy, so you can always double the number of sides. You see, that's why the power of 2 is cheap, but the essential information is there. Yeah. So that's the restriction. But you are beginning to suspect, I'm sure, that with origami you can do absolutely everything. So I'm going to show you how, by showing how to do a regular pentagon. To be sure, 5 is on that list, so you're not going to be impressed, but this will show you very, very cleanly how to do a regular pentagon. You take a strip of paper, and you make the simplest knot that you can imagine, just like so. Okay? And then you tighten the knot and flatten it. Tighten and flatten, very, very gradually and very gently. Tighten and flatten, and you keep tightening and flattening. And eventually, when you tighten and flatten sufficiently, you have something that is completely flat and completely tight. This is what it is. And now there's parts that are sticking out. I shall throw them away. And when I throw these away and show you what is really in the middle you see that you have a very, very beautiful regular pentagon. I didn't do anything. Nature took its own course. And it's a beautiful exercise to show that it is a regular pentagon. By the way, when a professor says it's a beautiful exercise, it usually means that he is too lazy to do this. But it's actually a very, very beautiful exercise. So that's a regular pentagon. Now, how do you do other polygons? You saw that when I made the pentagon, I made the simplest knot. So I passed through this knot once, so to speak. That's the simplest. What about the next level up in complexity? If I pass twice to make a knot, how twice? I'm going to show you a picture in a moment. But if you pass twice the next simplest knot, and then tighten and flatten, what you get is a regular 7-gon heptagon. If you pass 3 times, regular 9-gon, 4 times, regular 11-gon, and so on. So that's how it works. Here is a picture of that. And in fact, Professor Howison pointed out that this picture is wrong some time ago. But anyway, so regular 5-gon you see, but the regular 7-gon is drawn here. It's slightly sort of iffy. But the way to understand it, I think, is to draw a regular 7-gon already, if you imagine it regular 7-gon, and think that the inside is coated with a mirror. And like a ray of light, go into that 7-gon and bounce off the inside. Bounce, 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 and you come out. And that order of bouncing, how the rays sort of went over each other and so on, gives you a pattern of the tightening of tying the knot. And if you tie the knot that way and tighten and flatten, you get the regular 7-gon. Okay. So you see that one pass making a knot makes n equal 5, 2 passes n equal 7, 3 passes n equal 9, and so forth. So you have access to all the regular odd gons. But wait a minute. There's one number missing. What about n equals 3? How many passes do you think you must make in the knot in order to make a regular 3-gon? Huh? 0 pass. And indeed, that's it. You come in, you try to make a knot, but you don't succeed, and you come out. And then in that corner is a regular 3-gon hiding. So it works for all odd n. And once you have any odd n, then bisection is very easy. So you access now all n's. Yeah? So all n-gons can be constructed by this method. Okay. Here is a little lion that I folded. And when you open it, you see this, what is called the origami diagram. Don't pay too much attention to the blue and red, because those are the crease folds and the valley folds, and so on, the ridge folds and valley folds, sorry. But what is interesting is that you see it's some kind of graph, as mathematicians like to say, or a network. So you have lines and the points that are collected together. And if you look at any of those points, any of those vertices, there are so many lines that are coming in together and meeting at that point. Okay, let's count the number of lines. For example, there, you have points where 4 lines are meeting at each of those points, yeah? Okay. There is a point where as many as 8 lines meet. That's interesting. And a little further up, there is a point where 6 lines meet. It turns out that at any point, if you take a sheet of paper and fold it intentionally otherwise, and then squash onto a plane and open, there is some kind of graph or network that is drawn. At any of those points, there are always an even number of lines that meet. Now, I would like you to accept this, because this is actually the simpler of the theorems. And so the proof is not difficult, it's slightly tedious. For the experts in the audience, what's happening is that when I squashed, I produced what you might call a singular covering space, which has the front back pattern, which forces the parity. Okay, so that's actually easy. So let's accept this. So the simplest pattern is where you have 4 lines meeting at the point. Yeah, this is the example. Those 4 lines make sectors whose angles are alpha, beta, gamma, delta. So I'm going to give you a little present. A present is usually an object, and which costs money, is heavy, and when you go through airport securities, you get into trouble. But present that I brought it here for you today is a phenomenon, or to better said, is a mathematical theorem. And theorem, a phenomenon, costs you nothing, weighs exactly 0 gram, and when you go through airport securities, they are no wiser about it. So here is what it is. Let's fold the paper in with valency 4. And the simplest thing that you can do is what everyone uses before breakfast, and that is the square fold of the origami. So I'm going to trace the lines so that you see what is going on here and here. Okay, so it's 90 degrees all over the place. So that's very nice. But that was done very intentionally and deliberately. So if you did something much more randomly and generically, this is the pattern that you see. And when you open up, here are the creases. There's that, and there's that, and there's that. Those are the 4 lines. And so this is what it looks like. And those angles, which were randomly produced, cannot, however, be arbitrary. There is a very beautiful law that is satisfied among all those angles. So I'd like to show that as a present. Now, this camera is upside down, but it's not reflected. Does it look like my right hand? Yes, it does. So I have to write upside down, but not mirror reflected. So let's see. So this is alpha, beta, gamma. And you think I'm going to get into trouble drawing delta, but that's delta. Very good. Okay. Geez, this is the first time, do I have time for digression? Yes, I do. I always could write upside down, and also in the mirror image as well, in any writing system, Roman alphabet, Greek alphabet, Hebrew alphabet, Japanese scripts, and so on, Chinese characters. But when I used to teach in those tutorials at Cambridge, of course, I would have students around a very large oak table, and they were on the other side, and I would write upside down to do everything, including math formulas, no problem. And they were all very impressed, and that's the effect that I was looking for. But every year there were 1 or 2 students who noticed nothing at all, which is very interesting. But anyway, so where was I? Okay, so here is the theorem. Those angles are not arbitrary. And what are the laws of nature, mathematical theorem, that are satisfied? First of all, those angles must add up to 360 degrees. You wish that you said it, but I said it first. Yeah, so that's the simple condition. But the other condition is much more interesting. It is that the opposing angles, alpha plus gamma, should equal beta plus delta. So in this picture, if you look at the camera, alpha plus gamma must equal delta plus beta plus delta. For example, that kind of picture I drew there is impossible, however clever you are and hardworking you are, to create by folding and squashing a piece of paper, because the sum of that narrow sector plus that large sector is way too large compared with the remaining 2 angles. Yeah? So you cannot make this. That's impossible. So I'd like to prove that theorem for you, that alpha plus gamma must be equal to beta plus delta, by going back to how this angle was created. Okay, here I go. That's alpha, yes? Seen from the other side, that's alpha, but alpha equals beta plus delta, oops, minus gamma. Did you understand that? No, that was too quick. So let's do that again. So this is alpha, and seen from the other side, that's also angle alpha. But alpha consists of the superposed overlapped angles beta and delta. And so I have to actually subtract the superposition, which is what I counted too much, gamma, which means that the alpha equals beta plus delta minus gamma, which is exactly the same thing as that. QED. Okay. So in general, if you want to do an even number of angles that are collected at the point alpha 1, alpha 2, alpha 3, all the way to alpha 2n, so 4, 6, any even number, those angles are realizable by crumpling a sheet of paper and squashing, so flatten crumpling, if and only if there's a sufficient condition, if they add up to something suitable like 360 degrees. But the more important and interesting condition is that not the sum, but what the mathematicians call the alternating sum, plus alpha 1 minus alpha 2 plus alpha 3 minus alpha 4 plus minus must close to 0. That condition for 4 angles can be written like that too. You could write it as alpha minus beta plus gamma minus delta equals 0. And that's necessarily sufficient. Yeah. Now, what I mean is that if, for example, Professor Hitching gives me those angles, some numbers, real numbers, positive real numbers, and if they add up to 360 degrees, Well, probably he's a rather mischievous person, so he's going to give them to me in a completely wrong order. Yeah, but his granddaughter Olivia is a very nice person, so she's going to reorder them in the correct order. And if there is a correct reordering such that the alternate sum in that order closes to 0, then I can realize those numbers as angles by squashing a piece of paper. How? I take the largest of numbers that Olivia ordered, and then I start folding forward and back and forward, back and forward, back. And when I run out of the supply of the angles, I know, thanks to that closure to 0 condition, that I also run out of angles. Boom, I close, exactly. And then I crease, I open, and you have those beautiful lines coming out of the corner of the center, and those are the angles. It's exactly the same proof. Okay, and I keep saying it's a closure condition because this is, if you like, the manifestation, a shadow of the beginning of discrete version of homology. That's neither here nor there. Okay, so far we have been playing with mathematics, especially geometry, but now we'll gradually transition to physics. And from thence, we'll go towards engineering, physiology, and whatnot. And, you know, we really have to expand our field of investigation because the phenomena that we're talking about exist across all scales in the universe, from the smallest to the largest. For example, in the upper left corner there, I show you a photograph of a paper from Mino, from the region of Mino, which is a bit to the east of Kyoto. This paper is made in the following fashion. You take an ordinary sheet of paper, and then you wet it. And then you take a half-cut persimmon, you know, one of those fruits from Japan, kaki, and then you scrub the paper and stretch it out with persimmon. And once you have done enough of that, you dry it in the sun. And after it's dried, you wet it again and crumple, and then you scrub it out to make it flat again. And you keep repeating this process. And this scrubbing with persimmon enmeshes the small fibers of the paper so much that it becomes strong. And you can make from this Mino paper, you know, clothes, bags, even shoes that last for quite a long time. And those things are happening on a small scale, less than a millimeter long. Yeah? In the top right corner, you see one of my best friends, and you see that his trunk is lined with lots and lots of wrinkles. And they are best of biomechanical and thermal reasons why biology likes to make use of those creases. And that's happening on a scale, say human scale, between centimeter and millimeter, a few millimeters. And also, nature can play at this game of origami on a humongous scale. For example, that's the backbone of Latin America. That's the Andes. Yeah? How did this mountain range come to be? That's because on the one side, there was the Latin American plate. On the other side, there was a Pacific plate. To be precise, it's called Nazca plate. And Nazca plate started pushing against the Latin American plate. And you know what happens when one plate pushes against other, or there's some kind of compression along a paper, it just starts rising. And that rise is none other than the Andes. Yeah. And of course, your own Alps, because Africa is pushing against Europe, and Himalayas rose because India keeps pushing against Asia. And all those things have been happening on the scale of kilometers, or indeed thousands of kilometers. Yeah? And depending on how we manufacture these things, for example, if it's really humanly contrived, designed, it's called origami. At the other end, it's randomly produced by nature, you can call it crumpling. And in between, there's this really important sort of elemental phenomenon of buckling, which we shall come back to at the end of the talk. And the challenge is, can you actually extract science out of all this mess? For example, here you think you are seeing a photograph, you know, that looks like a crumpled sheet of paper. Well, for the good reason that this is actually a photograph of a crumpled sheet of paper. But what is it that we're seeing? You see, if you ask an artist to draw a crumpled sheet of paper, you realize that actually it's extremely difficult to find an artist who can. Leonardo da Vinci, I know, couldn't do it. Very few people can, because it's very difficult to draw a crumpled sheet of paper. You see, it's not enough to take a sheet of paper and draw a network, because a randomly drawn network cannot arise as a result of crumpled sheet of paper. There's already this story about the alternating sum being 0 but even if you satisfy that, that's kind of a perfect classification around each vertex. But of course, the interesting point is when you have multiple vertices, multiple points that are talking to one another via lines, and then there's an interesting, mysterious interaction that nobody has really studied. So among all the embedded graphs, or if you like, networks that are drawn on a sheet of paper, there's a tiny, tiny minority which can arise by crumpling a sheet of paper and flattening. What is it? Well, we who have lived in this universe long enough, I have lived probably longer than most of you, can actually recognize it immediately, but we haven't been able to verbalize this. I mean, nobody has. So what is it that we know which we can't express? That's the challenge. Okay. Well, next person, do you recognize him? He's furthest famous, perhaps, in the popular imagination than the previous two. But if you study mathematical sciences, at some point you keep running it. That's Simon Denis Poisson. Poisson equation, Poisson distribution, Poisson bracket, Poisson this, Poisson that. Now, he also left a contribution in what is called the theory of elasticity. And my purpose today is to teach you remind you half of the theory of elasticity in 45 seconds. Here we go. So take a block of material and you squeeze it in one direction. What do you think happens? Well, of course, it's going to bulge out in the transverse remaining directions. Yeah. How much it bulged out per how much you squeezed in, that ratio is called Poisson ratio. To be precise, you take the derivative, okay, differential coefficient. Or equivalently, you can pull the material, stretch it, and then, of course, it's going to tuck in its belly. How much it compressed in the transverse direction per how much you pulled out. That's the same thing, okay? So, bulge over squeeze. Now, for such a simple and important characteristic of the material, effectively, it characterizes the transverse response of the material to compression or dilation, yeah? For such an important concept, the notation in the literature is a mess. I mean, there are so many different symbols and so forth. For example, you'll see that Landau-Lifshitz, whom I'm going to cite in a moment, denotes it by sigma. Some people who should know better call it pi. Oh my God, I mean, pi should mean something else. Or p, lambda. Well, lambda is terrible because it should be Lamé constant and so on. There is absolutely no consensus on how to denote Poisson ratio. Now, after many years of living with me, my wife, Lisa Willis, finally found a God-given, or rather Lisa-given, notation for the Poisson ratio. Poisson ratio henceforth should be denoted by this. Alpha with a dot. In 200 years' time, I would like the history of science to remember Lisa Willis as the person who finally discovered the correct notation for Poisson ratio. Now, let's train our intuition. If you take that lozenge shape, so those black dots are supposed to be hinges, universal joints, and then those bluish lines are supposed to be rigid rods, okay? And if you compress that along the blue lines, blue arrows, of course you see that it's going to bulge out along the red arrows. That's a response of Poisson, and the Poisson ratio is reckoned to be positive. You can already assemble that simple thing into a structure, and you have a mesh pattern. And that is very interesting because, if you have a tissue with that kind of mesh pattern and make, say, a dress or something, it has the property that if you stretch in one direction, it hugs the body and it shapes very nicely and so forth. You can do the same thing with fundamental domains of unit cells, which are hexagonal, and then you have honeycomb and so on, and all of that is positive. To be honest, the Poisson ratio varies a lot from structure to structure, from material to material. But there is a very common belief that traditionally it's been believed that the Poisson ratio should be always positive. After all, it's kind of absurd to think of a material which, upon being compressed, sort of becomes smaller in the other direction as well. But when you pull, it bulges out. That seems to be wrong. There's some kind of thermodynamic stability problem there too. Mind you, there are actually structures which seem to have almost zero Poisson ratio. For example, if you take a spring and you compress it lengthwise, it doesn't look like it's bulging out in the transverse direction, but if you look very, very carefully, actually, it's becoming fatter. So it's almost zero, but nonetheless, it is strictly speaking positive. It's this belief that Poisson ratio should be positive is supported by the best of authorities. For example, this is Landau-Lifshitz. Landau, a prominent Russian physicist, wrote together with his student Lifshitz a monumental 10-volume series, Course of Theoretical Physics. And I don't know why I'm quoting the French edition, but because I'm visiting Colonel now, so that was on my desk. You see this cartoon picture of Landau preaching to his students. Daoskaza has a halo around his head and has angel wings, and he's telling truth about physics, and his students all have donkey ears, and so forth. Daoskaza, okay. So in the volume 7, which is devoted to the theory of elasticity, there's a footnote, which I shall translate as we go there. In fact, the Poisson ratio varies only between 0 and 1/2. So certainly positive, 0 and 1/2. We don't know of anybody in nature for which sigma, that's their notation for Poisson ratio. But do you know a better notation for Poisson ratio? Alpha with a dot. Okay, should be negative, that is, which will bulge out while being stretched. Okay. Well, faced with such great authorities and common sense, it's inevitable that we should be tempted to try to design negative Poisson ratio materials. And in fact, when you start looking for negative Poisson ratio, it's actually quite abundant. For example, instead of taking, as a unit cell, a hexagonal pattern, as we took before, let's take a hexagon, but a dented version of the hexagon and concave version of the hexagon there. And you can no doubt see that if I compress it along the blue arrows, it's going to respond by shrinking along the red arrows. That's negative Poisson ratio behavior. You can assemble them into a pattern, and it's already an interesting structure. You can also have other ideas. You think that these are just squares that are stuck together, but they're hinged in a strange pattern here. You see, when you start pulling any of the 2 points apart, those squares turn left, right in alternation. They all dance together and then expand nicely. And that's negative Poisson too. You can do it with triangular patterns, and there are 3D versions too. 3D versions are actually quite subtle. Okay. So the truth of the matter is not that the Poisson ratio is between 0 and 1/2. This is for isotropic material. That is, it doesn't depend on direction. All directions look the same. We'll come to anisotropic case later. Isotropic materials, it's actually not between 0 and 1/2, but -1 and 1/2. The upper limit 1/2 has a very clean physical interpretation. It's the incompressible limit, not be confused with the incomprehensible limit. So what it means is that if you have a material which doesn't want to change its volume, that's incompressible, thank you very much. Well, and if you squeeze it in one direction by 1, well, there are 2 remaining directions, right, in our space. So it has to expand by 1/2 and 1/2 in order to compensate for -1. Okay, in case you're wondering why I'm taking the trace, because trace is the derivative of the determinant. Okay, never mind. So in dimension D, it will be 1 over D minus 1. Okay. The lower limit, lower bound, 1 minus 1, also has a physical interpretation, and that is the unshearable limit. Do you know what shearing means? Take a deck of cards like that, and it's a rectangle, and put your palms at the bottom and the top. And while keeping them parallel, just slide them like this. That's going to deform the rectangular deck of cards into parallelogram. That's called shearing. Okay. And it turns out that when the negative Poisson ratio is negative, shearing becomes harder and harder. And that comes from a very simple theorem of mathematics, which says that any square matrix can be decomposed as written as a product of orthogonal matrix and symmetric matrix. And if you like, this is the generalization, if you have learned about complex numbers, that any complex number can be written as e to I theta times some r. So e to I theta is rotation, that's the orthogonal part, and r is the dilatation by some factor, that's the symmetric part. But much better to see all of that in pictures. So forget what I said. Just simply take that brown square. Let's say that you want to shear it into that blue parallelogram. You can do it in 2 steps. Step number 1. You take that brown square and you expand it along the diagonal, along the red, and you contract it along the anti-diagonal, along the blue, to make it into a losange, okay, rhombus. And having made that, you just rotate by a small angle, stonk into place. And that result, up to infinitesimal error, is the same as the result of shear. Yeah, so you can do it in 2 steps. But the first step, this one, becomes really hard when the Poisson is negative, because when you stretch it along the red, it wants to stretch also along the blue, and it resists your effort. Yeah? And at -1, it becomes absolutely impossible. That's why -1 for isotropic material is the lower limit. Okay, with that under our belts, let's go on to this person. That's Mr. Kyoto Miura. He's still alive with us, and he's a Japanese aeronautical engineer. In the 1970s, he invented a very beautiful origami pattern called the Miura Ori, which you see there. Okay? Now, I'm going to show you a Miura Ori for real. You know how annoying it is to fold a road map, a map. I just said something, but I realized many of you are very young. Do you know, maps used to be made of paper. You know this? I mean, it wasn't something you swiped. It was actually a sheet of, I know it's unbelievable, but it was actually a sheet of paper with pictures and letters written on this, yeah? And you try to open this as you are driving from, say, Oxford to Birmingham. Why would you? But you do. And on the road, you want to know where you're going, and then you open this. That's fine. But when you try to close it, it never folded back correctly. I mean, it started so creasing in the wrong places, making holes and so on. And next thing you know, your car is in a tree because you're no longer driving. And that's because this standard way of folding a map had too many degrees of freedom. But here is Miura-Ori. Here's a map, if you like, a sheet of paper. And you know to fold it back, all you have to do is to take any 2 points and just make them come closer together, and it collapses automatically in one way. Yeah? There's no degree of freedom but one. So I can just push these together. I can push these together. It's very, very easy. There's only one degree. And it's contracting in all directions at once. That is negative Poisson. Okay. So this property that somehow it's negative Poisson, and it has very few degrees of freedom that it's only. And they are very intimately related. There's another sort of property, which is hyperbolicity, which I'm not going to mention about this. Okay. I mentioned that Mr. Miura was an aeronautical engineer, and indeed, in 1997, the Japanese decided to put in orbit a satellite, artificial satellite. You know, one of the biggest challenges, the most annoying challenges of a satellite is what to do with solar panels or antennas. These must be very, very large in order to receive plenty of sunlight, or have enough resolution with communication with the Earth. But when you put it in orbit, you have to case them inside a small place inside the rocket, right? And once in orbit, you want to expand it. But after you have folded into such a small space, and once you are in orbit, you want to expand it, you know what's going to happen? You start opening it, and all the hinges go click, 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 and they get stuck, and you have lost, maybe milliards of euros and pounds, billion pounds. That's because it just got stuck. There are so many failure points. So the Japanese decided to design this folding pattern in Miura-Ori. And then when you open it in orbit, it's mathematically impossible to get stuck because there's only 1 degree of freedom. All you have to do is to grab 2 points and just pull them apart. It goes, just opens up automatically. And if you are interested in closing it, you can just push them together and then close it back together. So that has been tried. Okay. Now, so far I have been mostly talking about isotropic, so direction-independent properties. But now I'm going to discuss 1 or 2 direction-dependent properties of a material. So here is an experiment. I'll try to show you that. Excuse me. You don't want to see my face. So I shall hide them. Those 2 squares were cut out from a single sheet of paper on my desk at the École Normale in Paris. A single sheet of paper. So these are twins, if you like. They come from the same material, made of the same paper. Yeah? And if I put them together and clamp them on one edge, and then hold them in space like that, they sag a little bit, and they sag exactly in the same manner because they are exactly the same material. Yeah, they come from the same sheet of paper. So they respond the same way under gravity, they sag. So they stick together, of course, because they're sagging the same way. No surprise. But now, when I turn them over, they separate. On one side, they stick together. On the other side, they separate. They come from the same sheet of paper, those 2 squares. But that's not the only surprise. This is the separating side, and the other side was the sticky side, yes? Now, keeping them on the separating side, I'm going to migrate the clamp on the next edge and hold them. This was the separating side a moment ago, but this time, if I support them on this edge, they stay stuck. And the other side, which used to be the sticky side, now becomes the separating side. What is going on? Very good. So because I'm very fond of toys, this is a toy, but I brought a toy of a toy. This is a secondary toy. If you make a square and fold it an accordion pattern like this, this accordion has a wonderful property that in one direction it is very, very flexible, but in other direction it's completely rigid. So rigid that actually I can support a weight. Yeah, it's completely rigid. And for those of you who are interested, the fact that I creased in one direction means that if you try to bend in the other direction, it produces some non-zero Gaussian curvature, which paper doesn't like. I'll come back to that. Okay, so this is a way of rigidifying a sheet of paper or any membrane just by creasing. Okay, so what I did when I had in front of me that sheet of paper is very simple. Paper has some anisotropy, that is direction dependence, because fibers are running this way and that way. Who knows? Because of the manufacturing method of paper. After all, however, I cannot see this microscopic structure because I don't have a microscope. But it doesn't matter. I just cut out two sheets of paper, like so, and when I assembled them, I turned one against the other by 90 degrees. Because then, look what happens. If I support them like that, what is rigid is supporting underneath what is flabby above, so they stick together. But when I turn over, they separate. Yeah? And when I migrate to the other side, the next side, the sticky side, and separate inside, exchange their roles. So I didn't know what the microscopic structure was like. I couldn't see it. But by playing the microscopic structure one against itself, I extracted a macroscopic response that I liked. Okay, so this is kind of a magical trick which gets the macroscopic response from microscopic structure without knowing what the microscopic structure looks like. Okay, so this is how it was done. By the way, I showed this to my friend Steve Childress at Grant Institute, and he does the New York Times puzzle crosswords. By the way, he does it on paper too. I know newspapers used to be made of paper too. Yeah, and he says that when he wants to keep some crossword puzzle, he tries to tear it with his hand, and one direction is much easier to tear than another. So I wanted to repeat that experiment, and here it is. In the long history of your august institution, it's probably the first time that the public lecturer brings in toilet paper into a lecture, and I harvested this over there a moment ago. So if I try to tear it lengthwise, it's very, very easy. It goes really straight. But if I try to tear it sideways, I'm trying to do it very, very carefully, but actually it's basically impossible to tear it straight. It goes all over the place, excuse me. Yeah, it's really a mess. Yeah? And that is a manifestation of microscopic anisotropy of paper. By the way, I can't help pointing out that at Oxford University, at the Andrew Wiles building, the toilet paper tears very easily lengthwise, but sideways it's impossible to tear. It's something to think about. I'm not saying it. Okay. So let's now make a detour. It's actually a final detour through a very, very contemporary geometry. It's really the day before yesterday. Here's a strange question. Take a sphere. By the way, you might know that the modern mathematicians like to distinguish between sphere and ball. When the mathematician talks about a sphere, it's almost always a spherical shell. Yeah, there's nothing inside. Inside is hollow. It's just a shell. And the ball is the stuff inside it together. So that's called a solid ball, if you like. So this is a spherical shell, two-dimensional spherical shell, sitting inside of 3D. Can you, if you like a big pimple ball, can you put that kind of sphere into a smaller space like that? The answer is yes, you just crush it. Without crushing. That is, without changing length along the surface. Yeah? That's called isometrically. Can you do it without changing any length? And the answer should be no, because you see, after all, when you try to make something smaller, you must start denting it. Yes? And when you dent like that, you create a crater, and the region of the crater has what is called Gaussian curvature 0. Whereas the Gaussian curvature of a sphere is 1 over radius squared. And so you change the Gaussian curvature, which cannot be because that's not an isometric operation. If you like, there is a way of measuring curvature, yeah, which you learn in university in the second year or so, and which prevents you from doing this, yeah, because whatever is isometry, measure sort of length preserving, has to preserve the curvature. So it's impossible, it's prohibited by curvature. But then, another funny thought occurred, which is that, okay, so if you, again, learn about curvature, you see that there is a formula for the curvature, and you have to have the second derivative. You know, you differentiate once, you differentiate twice. And you combine these second derivatives, and that's the formula for curvature. What if we tried to do this isometric embedding, as we call, of a large thing into a small thing, with surfaces that have only one derivative, first derivative. What do I mean? Well, it's not smooth enough. It can be differentiated once, but not twice. Because then what's going to happen is that Professor Brouillard is going to come and say, well, Tadashi, you can't do this isometric amendment because curvature gets in the way. And they say, what curvature? You cannot calculate it because we have only one derivative, not two. That sounds like really kind of, quibbling. But in fact, this is one of the bases for the great work by Nash and Gromov, that's in Beautiful Mind, and for embedding isometrically a large thing into a small thing. And that's using only first derivative, but with that surface, which is kind of smooth, but not too smooth. Okay. And more recently, that was an existential proof theoretically, but a French team, Thibert and Borelli and so on, they were based at the time, I think, in Grenoble, actually implemented this and found an explicit algorithm that puts a large sphere into a small space. And it was a really concrete construction because they made a model out of concrete, you see. So this is a halfway model. As you can see, what they did was what they do is to twist the sphere. And as you twist, it develops all those corrugations, wave patterns. But if you look very closely at each of the corrugations, that's lined with more corrugations and more corrugations. This is a nested pattern all the way down to the infinitesimal. Yeah? And when Borelli came and showed me this, I said, I have seen this somewhere before. That's the twist version of Miura-Ori. So I shall show you what that is. Take a sheet of paper. All my demos start with the phrase, take a sheet of paper. Yeah. And two cans, cylinders. And I'm going to roll up those cans and roll the paper around those cans, but while leaving a little bit of gap between those cans. Is that okay? So I roll them very carefully. And having rolled them tightly, I twist one can against the other and then squeeze. And when they're open, I see a rather beautiful pattern that is produced here. Yeah. And this, there's a lot of geometry in a zigzag pattern and so forth, but all of that is determined by only one dimensionless parameter, which is the gap between those cans divided by the diameter. There's nothing left. And this is critical because while I'm sort of squeezing, there's a lot of physics going on, some functional being minimized and whatnot. But at the end, when you squash, there's only geometry left. That's very, very typical. Yeah. But anyway, at the end, you see this pattern, and that is very much like the pattern that we saw there. And for a good reason, I think, because what did I do? I trapped between those two cans a little bit of paper, and I told nature, well, you have to go into a much tighter space. Yeah? Put it in a smaller space. And nature really doesn't want to do it. But if it has to do it, it wants to do it as isometrically as it can. Yeah? Because not isometric, it costs it energy. So that was the nature's response to how to put the large thing into a small thing as isometric as can. So, Nash, Gromov, Borelli, Thibert, these are wonderfully imaginative and intelligent people, but we didn't have to ask them to do this. We could have asked nature to do it. So I'm proposing that this is something called H principle. You could do actually a physical version of H principle. Okay. Now, another thing that I wanted to show before moving on is something that is related. So this is actually a beautiful thing that I learned from Alcock, I think David Alcock, who's no longer here, but he's probably retired at Oxford. And it's called the Momotani carpet. And this particular one, actually, I folded on a long, long flight between London and Cape Town. I used to go to Cape Town to work at the Ames, some of you know, and also at the nursery school, which I helped to found and run for HIV-positive babies in a slum next to Cape Town. So it used to be a very, very long flight between London and Cape Town, and 14 hours or something like that. But so one day I learned this from Alcock, so I decided to fold it. I started from a largest sheet of paper, about yay large, and then as soon as I got on the airplane and I started folding it, my neighbor was rather worried about this, and so of course I didn't fold for 14 hours, maybe 90 minutes or less, because it's just a repetitive pattern or something. But at the end of the day, and there's some coffee stain there, and what happened, was produced is this. I pull this. Watch what happens. Whoop, 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 whoop. And on the other side, something dual is happening. Whoop, whoop, whoop. And that is very beautiful, but that's not all. When you see, this is made from a single sheet of paper, and paper is not particularly elastic, right? I mean, just, but when I pull and release, it actually has, it's bouncy, yeah? Boom, boom, like a spring. So it is a way of putting effective elasticity into a sheet of paper. It's quite interesting, right? So that's called the Momotani carpet, which was invented by another Japanese engineer called Momotani a long time ago. But there's another story about this, which is that at Stanford, I have a very close friend, Prakash, and he's a MacArthur Fellow and all that. And he recently had a very, very sort of bad sort of hospitalization experience, and he almost died. Fortunately, he survived. But he said that in hospital, they had to put a tube down his esophagus, his throat. And that was extremely sort of unpleasant, he said. So we started talking in the hospital, and I thought, well, it would be nice, not necessarily this one, but something that has negative Poisson ratio. You see, it has negative Poisson ratio because when I pull, it expands in all directions, yeah? Something negative Poisson ratio, if I wrap it around into a cylinder like this, into a tube, oops, sorry, like that, this would have the funny property that, you see, when you compress this tube lengthwise, it will shrink. And when you pull, it expands. The opposite of what an ordinary material would do. After an ordinary material, when you compress it, becomes fatter. When you pull, it becomes thinner, right? But it's the opposite. So if you could make, of course, not that particular one, but if you could make a negative Poisson cube, then you can push it down your esophagus. And because it's going to be in compression, it will shrink and it will be very thin and it will go down smoothly. And once you reach the top of the stomach, you just tug, and that's going to be in tension. It expands and hugs the inside of your esophagus. That would be a nice thing to do. And there are some other sort of applications to maybe design stents in your arteries and so forth. Okay, so it's time to now summarize some of these things in a theoretical fashion. So here's a typical photograph of a Miura-Ori. In order to simplify the discussion, let's say that each face of Miura-Ori is a losange, a rhombus. In other words, all the edges have the same length. I can do it in general, but this will simplify the formulas. Well, a Miura-Ori in any state is characterized by two angles. One of the angles shows its geometry, the other angle shows its dynamics, if you like. Geometry is represented by alpha. That's the angle in a corner of each face. So if alpha is almost 90 degrees, each face is almost a square. If alpha is small, it means that each face is long and thin. Okay, so that's just the shape. Theta, on the other hand, is the angle between two adjacent faces, neighboring faces. Yeah. So if theta is almost 180 degrees, that means that I have stretched out the Miura-Ori, almost flat. And if theta is small, that means that I have compressed it. Okay. So that's what. So any sort of Miura-Ori, and in any state, is characterized those two angles. And in that state, it's not too difficult to compute the Poisson ratio. That's what it is. It's 1 minus something that is larger than 1. If you know anything about science, it's 1 over sine times sine. So it's going to be a negative number. And by playing with alpha and theta, those angles, I can actually hit any negative number whatsoever as the Poisson ratio. Now you're going to object, wait, what about that theorem that I told you about, which is the lower bound is -1? That was the isotropic case. Yeah, this is anisotropic. It's very, very much direction dependent. So that's allowed. Okay, so you see, it's interesting. A single Miura-Ori in some state will represent any negative number as the negative Poisson ratio. But there's more. I mentioned earlier buckling. But you know what buckling is? You take a rod and then you just compress the ends. And if the load is very light, the rod contracts elastically, just shortens. But when you put the critical load, well, rod can't take it anymore, boom, it buckles out. Very large deflection sideways, and that's called buckling. And Euler and people study this, but that's a one-dimensional thing. What about the two-dimensional buckling? What I mean is you take a membrane, and at each point of the membrane, you apply a homogeneous and isotropic compression. How do you do that? It's actually quite difficult because if you start pushing the edge effect becomes very noisy and so forth. So you might have to use moisture, you might have to use thermally, whatever it is, but you do the compression. And for very weak compression, the whole membrane shrinks in its own plane. That's fine, but at some critical load, the membrane can't take it anymore, and boom, buckles out into the third dimension. And that buckling pattern turns out to be Miura-Ori. So again, Mr. Miura, extremely imaginative and intelligent person, but we could have asked nature to invent this fold. So far from being just an example, Miura-Ori is actually the simplest and universal model of negative Poisson ratio. Yeah? At this stage, actually, I realized something. You see, there is a much, much easier way of producing negative Poisson ratio behavior. So far, we have been very clever and very hardworking, try this, try that, we study this and investigate that. But there is a much, much easier way of doing it. Take a sheet of paper and just sample it. And when I pull it out, it expands in all directions. That's negative Poisson, isn't it? Now, those of you who are very careful will say that, well, bird's eye view will show negative Poisson, but if you look at it sideways, when I crumple, it actually thickens. So that's not negative Poisson, but I'm going to counter this. For any sort of allowable error epsilon, I can actually do this in a gap within epsilon by increasing the wave number, if you like, by having lots of increases. So quantitatively, within epsilon error, for any arbitrary small epsilon, I can do this at negative Poisson ratio behavior. And of course, it is negative Poisson because I made it that way. I crumpled in all directions. So of course, when I expand it, it expands in all directions at the same time. And look, this looks really random, right? As random as human can be. And of course, each point, as I said, earlier, satisfies this mysterious alternate sum zero condition, whatnot. And the rest of it is kind of unknown to science at this moment. But it looks very random. And it's negative by construction. And on the whole, statistically and on the large scale, it is homogeneous and isotropic. So this leads me to a bold conjecture, which is in boldface, by the way. Until recently, people thought negative Poisson behavior didn't exist. And if it did, it was very, very freakish and artificial, but far from it. It might be that if in this universe, you take arbitrary and random structure, you might have, with high probability, in the majority of cases, negative Poisson ratio behavior. And the reason is, look, this is really a prototype of random structure, right? Crumpled sheet of paper, and that has negative Poisson ratio. Negative Poisson ratio. Okay. It's time to wrap this up. We scientists, as well as the general public alike, have the impression that science takes place, mathematics included, in a very, very specialized context. You might go to a lecture and some professor is haranguing you, and then okay. But when the examination is over, you close the book and you go out of the room, and the institute is closed, and you go on holiday. Science ceases to exist. Yeah, that's the impression we have. So science is something special that we do in some context to show off, to have money, and so forth. And that happens in labs, institutes, and on the internet and in the libraries. You go looking for information, and of course nowadays, you have to apply for big research grants, and in order to do so, you have to draft cutting-edge proposals saying that, well, I'm going to achieve this, I'm going to achieve that, and so forth, and so on. All of these are supremely important because that's where we expect science to come from, obviously. And on the industrial scale, as a matter of organization of society, we have to do this. But against all this background, you are perfectly justified to ask, well, Tadashi, why are you playing with paper then? Yeah, as in guise of an answer, I'd like to share with you a little read passage of Aristotle. Yeah. In this passage, which comes from the Partibus Animalium, and this is the Dies und Kant's Presocratic Philosophers, so the collection 22A9. Aristotle is telling a story about Heraclitus. So this is the Heraclitus, who was one of the Presocratic philosophers, if you like, natural philosophy, about 600 BC. And he was, a science star of the time. So equivalent of a professor of mathematics at Oxford University nowadays. And so one day, two young people wanted to come see Heraclitus, Aristotle tells. And those people obviously expected to see a science star, typical, stereotype. Probably somebody wearing a lab coat and a long beard, and sitting at a supercomputer console and coding with huge sort of sort of distributed programming and so forth, or maybe lecturing to 1,000 people, or running a lab where everyone has his place and sort of hundreds of people experiment on something or other. And so this is what they expect Heraclitus to be. But when they arrived and saw Heraclitus, they found a completely different person from what they were expecting. Okay. This is Aristotle speaking and my free translation from Greek. In all natural things, there is something of the marvelous. There is a story that some visitors once wished to meet Heraclitus. But when they entered and saw him in the kitchen, warming himself at the stove and playing with children, they hesitated. Is this Heraclitus? I mean, warming himself at the stove and playing with children of all people. But Heraclitus said, "Come in, don't be afraid. There are gods even here. It's been a great pleasure and privilege to address this wonderful company. Especially, I would like to thank Professor Keating, Professor Brightson, Professor Strafethen, Professor Brouillard, and all my friends for their very kind invitation. Thank you very much."